So today we're going to be talking about a preliminary test what on our series on special relativity, and in this case we're going to be talking about four vectors. So what is a four vector? Well, a four vector a vector with four components that transforms via the Lorentz transform. So a four vector is a vector that with four components that transforms under the Lorentz transform. So how exactly would you write a four vector, and how does it differ to the normal three vectors we see in classical mechanics? Well, the difference is that, usually with three vectors, you can always define some vector, let's call it x, which is defined as x1, x2, x3. Of course, this is x, y, and z. Whereas with four vectors, let's call it x, which is equal to x0, x1, x2, x3. So yeah, as you notice that the main difference is that this vector has 4 dimensions and this one is 3. So what exactly would this fourth dimension be? Well, let's just say this would, x0 would just be equal to ct, which is basically a temporal component, which is basically pretty much the speed of light times time. So meaning that you could replace this with ct x, y, z. And first, if we want to actually do operations with four vectors, then we actually have to create a different notation rather than the arrow if we want to distinguish between the four vector notation and the three vectors. So we're going to go into index notation. And we're going to talk about covariance, indices, and contravariance. Indices. So covariant indices are usually denoted by, x mu. So basically we're using the mu to determine the component, and this is what a contravariant four vector would look like. And not contravariant, covariant vector. So this is contravariant. No, not, oh my god, it's covariant, not contravariant. And this x mu is covariant, not contravariant. So why are we making this distinction between covariant and contravariant vectors? Well, it's because they're related by a tensor. But before we get into that tensor, let's talk about what exactly is a tensor. Well, so let's talk about tensors. A tensor is an object that obeys certain transformation rules and is left unchanged. So how would we write tensors in index notation? Well, in this case, we would usually write, with contravariant indices, we'd write t mu nu. So as you can see, a tensor would have 2 indices as opposed to 1. And with covariant indices, it would just be, of course, t mu nu. And the tensor we're going to be talking about is going to be called the metric tensor, G mu nu. But basically, the goal of the metric tensor is to raise and lower indices of other tensors or 4 vectors. So in this case, we can relate the contravariant indices to the covariant indices by x mu being equal to G mu nu x nu. And why are we, and when you see an upper index multiplied by something with a lower index, you sum over that index. So this would just be equal to G mu 0 x0 plus G mu 1 x1 plus G mu 2 x2 plus G mu 3 x3. So that is kind of what this means. And we don't want to write all of that, as we want to make it in a compact form. And usually, when we're creating this thing known as a dummy index, we're pretty much lowering the rank of a tensor. And this brings rise to dot products in index notation. So basically, we would denote the dot product with x mu, where since all of the indices are being summed over, that would just yield a scalar, which is equal to x0 plus x1. So yeah, this would yield a scalar. And how exactly would we compute this dot product? Well, we have a definition of x mu in terms of the lower index. Well, it's going to be x mu G mu nu x nu. And well, in normal Euclidean space, G mu nu is equal to the Kronecker delta mu nu. But we're not in Euclidean space. We're not in 3-dimensional space. We're in 4 dimensions. So G mu nu, upper index is mu nu is equal to, and we're going to be using the minus plus 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 convention. So minus 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So all of the time components, x0, this just leads to x1 squared plus x2 squared. x1 squared plus x2 squared plus x3 squared minus x0 squared. So this is the dot product of 4 vectors. And we have to understand the dot product of 4 vectors because it's not necessarily just an upper dimensional version of the free vectors product. Rather, you have to have because the metric tensor is not equal to the identity. So how would this actually apply to relativity? Well, usually we have our free position, which is x vector is equal to, well, of course, x1, x2, x3. Of course, in this case, we're using covariant indices. And, well, this time, since we have 4-dimensional space-time, is equal to x0, x1, x2, x3. And this could be applied to other vectors too, not just position. V mu equals to v0, v1, v2, v3. And pretty much any vector that is considered that is not a pseudovector. What is a pseudovector, you may ask? Well, a pseudovector is a quantity that isn't necessarily invariant under all transformations. Why is this important? Well, usually most terms we have for usually the free vectors in normal classical mechanics. Usually they're normal vectors, so we can change them to 4 vectors. So we of course, position, velocity, or momentum. But some quantities, that is usually ones that is one that usually has been defined as the cross product, that is angular momentum, angular velocity, etc., are pseudovectors. And why is this important, you may ask? Well, if they are pseudovectors, then you can't necessarily apply the transformations like the Lorentz transform. So meaning that you have to replace the cross product, that is, L is equal to R cross P, to the wedge product, instead we just L equal to R wedge P, where the wedge is equal to R this times P minus P R. So what is the tensor product? Well, this is called the tensor product, but this is a product which yields a tensor, of course, which is basically just like R0, 0, no, not R0, 0, R0, P0, R0, P1, and P1, and etc. And pretty much all of the components turns into a tensor. And the wedge product is just this is just R tensor product P minus P tensor product R. And usually in index notation, let's say we are working with, let's say you're just working in free coordinates, for example. So Lij is equal to Ripj minus Pjri. So you can see that it's kind of because since no indices are being summed over, this quantity is by definition a tensor. And of course we can extend this to 4 dimensions, so L mu nu is equal to R mu P nu minus P mu R nu. And we have to turn pseudovectors into tensors so that we can actually transform with them. And this concludes our lessons about 4 vectors. Thanks for watching, and I'll see you later.